All right, so first of all, this says that there's going to be a wire that has a circular loop and it's carrying a current. Okay. Now I actually want to start this problem off one step at a time, and I just want to look at what it would be if it was a straight wire alone. Okay. Now it was discovered that current carrying wires will create magnetic fields. So there's this close interplay between magnetism and electricity. And the type of magnetic field that it makes is going to be concentric circles around the wire. Okay. So what can this magnetic field do? Well, one of the simplest things that it does, and the way that it was discovered, was that the current carrying wire will deflect a compass. So let's say that you have a compass. Let's put the compass right here. I'll try to draw this in 3 dimensions. The compasses that I've drawn are supposed to be in a circle around the wire, with the wire at the center. Now normally, the compasses would all point the same direction, as long as there was no current. So let's take the current away for a minute. And let's let the compasses just point toward geographic north. Okay, that's what would happen if no current was flowing through the wire. And I hope it's clear that, there's a certain distance from the wire that all these compasses are. It's a distance of radius r, let's say. And then you flip on the current in the wire. And we have 1.6 amps flowing through it. Then what happens is the needle's positions will change. They'll go to new positions. They'll be deflected, in other words. But which direction will they be deflected? Well, we can actually determine that according to what's called the right-hand corkscrew rule. They would be deflected in a clockwise fashion. And they would tend to point in, that clockwise circular pattern. And what this means is that there is a magnetic field. And it's going to be a loop or a circle. And that's the direction of it. Okay, now how did I know that that was the right direction to use? Well, we have this right-hand corkscrew rule, which says you point your thumb in the direction of current. And then you're supposed to wrap your fingers around the wire. Okay, so thumb points this way. And then you just wrap your fingers this way. Grab a hold of the wire in your mind with your right hand. Okay, and you can see the curvature of the fingers, right? The way that they're wrapping around is the way that the magnetic field wraps around the wire as well. We want to be able to show that in 2 dimensions as well, right? So when we do it in 2 dimensions, we don't have the option of drawing like a concentric circle like I did. Okay, so instead, in 2 dimensions, what we do is we say anywhere where the fingers are pointing out of the plane, of the paper, then we'll use dots to represent the type of magnetic field that's coming out of the page toward your eye at those points. And then wherever the fingers are going into the page here, then we'll use X's. All right, so just be aware of that convention, that if you see a two-dimensional current carrying wire in a plane, and if you see dots up here, that means the magnetic field is coming out toward you at these points. Okay, so it's called out of the page. And down here we would have X's. And that's into the page. And all it means is that's the direction that a compass would point if it was located at those different positions. Okay? And that would be, yeah, for a current carrying wire. All right, we have a letter for the magnetic field. It's B, capital B. And it's going to be measured in what are called Teslas. Capital T. All right, so we'll try to do a calculation here. This one says that the current is 1.6 amps. And let's say that we want to find the strength of the field at a certain distance, let's say a point P below the wire. Okay. We actually have a formula which will give us the strength of this field. Okay, so it's B equals mu naught I over 2 pi d. All right, so I'll go over each of the symbols here. Mu naught means the permeability constant, and it's 4 pi times 10 to the minus 7 Tesla meters squared per amps. D is the distance from the wire. Okay, so this is D. And in this particular problem, I'm going to use that radius of 50 centimeters to be the distance. Okay, so D is 0.5 meters. I is, of course, the current. Okay. Okay, so let's go ahead and do this calculation. So we need B equals 4 pi E minus 7, 1.6 amps over 2 pi times 0.5 meters. All right, I'm getting 6.4 times 10 to the minus 7 Teslas. Now this formula doesn't give us the direction. We have to be able to find the direction. And one way to do that is with this right-hand corkscrew rule. We already did it, because I drew the X's below and the dots above. So our magnetic field is going to be directed into the page. Okay. Now, if the problem had given a coordinate system, such as positive X, positive Y, And they'll even give the third dimension now when we're dealing with magnetism. Then you'd want to be able to express your magnetic field in vector form and say that it's 6.4 times 10 to the minus 7 Teslas in the negative K direction. Okay, so that's something we'll use quite a bit with magnetism because it's fundamentally a three-dimensional phenomenon. Okay, so now we want to make the problem just a little bit more complex here, because the current carrying wire has a loop in it. All right. And we like to find the total magnetic field due to the superposition of the loop and the straight part of the wire as well. See, the thing about a current carrying loop is it can also create a magnetic field. So now let's try the problem as if it was just a loop of radius 50 centimeters carrying that same current. Well, what would happen then? Okay, so if you have a current carrying loop, let's say it looks like this. And let's say that our current is 1.6 amps. And it's going around in a circle like this, right? Now you can imagine doing the right-hand rule on that loop. So you have to grab the loop, letting your thumb go in the direction of current, though. Okay, so there's my thumb. My fingers will wrap around the outside edge here. Okay, and then look what they do. They point into the page on this side of the wire. But when they wrap around here, they'll be pointing out of the page. So I actually would want dots on this side. Okay. If I grab the wire in a different position, like say up here, and I want my thumb to point in the direction of current, right? Just imagine doing that, and this is what you see. Your fingers are always going to penetrate through the middle of that loop. See? And then when they come out the other side, they point out of the page. So we have dots on the other side. What this does is it creates a fairly uniform magnetic field on the inside of the loop. Okay? And that has its own formula as well. All right, so the formula due to a loop is a little different. Mu naught I over just 2R. Okay? So it depends on the current and the radius. All right, so we're going to have 4 pi times 10 to the minus 7, 1.6 amps over 2 times 0.5 meters. The magnetic field at the center of this loop is going to be 2.01 times 10 to the minus 6 Teslas. And if we want to make it as a vector, we could do negative k hat into the page, in other words. All right, so this was the field due to a wire right here. And this is the field due to a loop. So maybe you can imagine what we'll do for this problem is we have to combine them through superposition. Same as with electric fields. So if we want the field at point P, it's going to be the B of the wire plus the B of the loop. So 6.4 times 10 to the minus 7 Teslas plus 2.01 times 10 to the minus 6 Teslas. Add them together. I'm getting 2.65 times 10 to the minus 6 Teslas. All right, what would happen if we had more turns in the wire? So you can imagine that the more turns you have, the stronger the field becomes. Because of superposition, right? So if you do this and let the field due to all of these coils add up, then what you get is a stronger field. Okay, and so the formula that I gave for a loop, that was just for one coil. Okay, or for one strand, let's say. The full formula would be mu times n times I over 2r. So what does n mean? N is the number of turns. So if they're talking about having 4 turns in there, then our calculation is going to become 4 pi times 10 to the minus 7, 4 turns, 1.6 amps over 2 times 0.5 meters. All right, then I get 8.04 times 10 to the minus 6 Teslas. That's just for the coil part. If I want the field due to the whole thing, then I have to add them. So 8.04 times 10 to the minus 6 Teslas plus 6.4 times 10 to the minus 7 Teslas. Yeah, I'm getting about 8.6. All right, so the point is, different geometries will have different formulas when it comes to magnetic field, and we can have different contributors to the magnetic field as well, and we just want to add them together through superposition.